Today we'll talk about sampling and parameter estimation. So this is last week we talked about the probability. Basically, we know the distribution in this box. We know the proportion of black is 3/4, and we want to find a lot of probability. If we draw the 10 chases from this box, how many chases will be, what's the probability to have 2 black or 3 black, something like that. So today I have this box. In this box, I don't know. I don't know what's the proportion of black in this box, but I want to find out. Many times, like the yield of a variety, we don't know the yield. We wanted to make some experiment to find out. So in this box, let's say, of course, if you don't look, I just tell you, in this box, I have some black or some white. And our purpose is to find out, the proportion of black. How we can, find out that proportion. Again, before we know the proportion, and we can know, if we make a 5 experiment or 10 experiment, and this represents the a number of black. Number of black can be from 0 or 1 up to n. If we know this proportion, we know the probability for the b equal to 0, b equal 1, or b equal n, right? So, this is just one example, because we know the distribution is binomial, and p is p equal 0.75, and n equal anyway a given number. So that's the probability. But now we in this box again, it's a binomial distribution, but we don't know. We don't know the p, but we wanted to find out. Normally, how we can find the p value in this box. Again, the p is treat this as an infinity population. We wanted to find the proportion. Then we needed to draw some sample. We needed to have some data. Without any data, I cannot do anything. So let's say if again we make a 5 experiment, and then I use the curve represent the number of black. If you draw 5, and then let's try. Don't look at the box. Just take 5 chases out. 5. We do so one, then it means you have some missing data. How will you like it? So in the 5 chases, there's 1 black. So what is the best guess about the proportion of black in this box? So we make one experiment. We draw 5. We have the black equal to 1. So what's the best guess? What's the best guess about the p value here? No idea at all about black or white. Oh, it doesn't matter. If you know black, then everything left is red. There are only 2 colors. 2.75. You said p is equal to 0.75. Why? Why you give this estimation? Any reason? Well, we needed to have some reason, We needed to have a good estimate. Many times we want to do some prediction. We want to the prediction make sense. Why you say I give a hat? You know, this is an estimate. So this like the if without a hat, we see it a true value. So any other estimate, if we from the 5 choices, we got one black. So if I ask you, to estimate the proportion of black, what's your guess? Okay, you said what? 0.2. Why? Five equals 1 white. Yes. Okay, so this is exactly, so from the, this total sample size, we got a number of, this number to be black. So this actually, this is a better estimate than this one. Well, this one, because you cannot give any reason. We have any reason to have the 3/4 here. But this one have some reason. This one use the samples we draw, use the data we have. Got it? Okay. So then this is, as I said, if we know the distribution here, so everything here is a probability. That's a probability. Probability. So if we don't know P, and now we have some data, we have some sample, and based on the sample, we give a reasonable. This have some reason, If there's one black in fact, the proportion is 0.2. So this is about the statistics. Okay, statistics is about we needed to have some make the sampling. We needed to collect the data, and then we wanted to estimate the summation. But do we really think the P is equal 0.2 in this box? Not sure. Not sure exactly, because if let's say a message up, if we make another fifth sample, fifth sample, and try to make it up, this is like a randomization. This is like a randomization. Okay, you think of that. You're going to look at the box. Okay, so but in another experiment, there are two black. The same box. Remember, this is the same box. So another sample we have two, and then we have the estimation here is 0.4. Right? So this is exactly why I give a hat here, because for any replication, this is like a this is like a replication. This is the the replication 1 and the replication 2. Replication 2, I have another estimate. But if we can have only one replication, of course, this is the best guess what we can give for the proportion of black in this box. But please remember, this estimate have an error. This estimate is not exactly equal to the true value of the P. It's just an estimate. So now you have some idea the difference between the true value and the estimate of the true value. Why we have, this is the true value which we don't know. It's a given value. If we count everything in this box, we will find this. Basically, I put an equal number of black and white. So the true value here is 0.5. But sometimes we can have an estimate 0.2, sometimes 0.4. Is there any way we can improve? No. Is there any way we can improve the accuracy of this estimation? Please guess how we can. This look at the still come from the same population, but we see the variation is high. How we can reduce? How we can have a better estimation of the p? Okay, exactly. We increase the sample size. So instead of 5, if we draw 10, or if we draw 20, so we use the same formula, but that estimate will be much, much convincing. Let's say we can put the case to there, but one case we only have 5 sample sets. But another case we have 10. Of course, we can have a more larger. So which estimate is better? Or you will like? Of course, we like this one. So this is exactly the importance of sample sets in statistics. Why we want to have to make a replication. The replication can increase the accuracy of the estimate. So I use the binomial as an example, but the principle applies to any distribution, no matter it's a normal distribution or any other distribution. So I think that's a very important statistical concept. We should be keep that in our mind when we make any experiment in the future research. Yes.
For example, you have this box and you also don't know how much you have white and black samples.
Yeah.
And then you check for maximum 30 numbers. And you do 2 replications or 3 replications. Every time you get, for example, first time you get maximum white and second time maximum black. And third time, one of them. And then what you can predict, either in the box, the ratio is 1 by 1 or 3 by 1 or 1 to 1. How you predict?
Okay, this is exactly the question we are going to talk next week about the hypothesis test. So we can give this estimate. So we can test how far, whether they, given this value, so this value, how much we can say the true value is equal to 0.5. How likely? No. Or if this estimate has some significant difference with the 0.5, which is something you said. So that's the hypothesis test. Once we have this value, maybe we want to test whether this box have equal number of black and white. Then the p equal to 0.5. So basically, we are going to test the hypothesis. We're going to the hypothesis H0 p equal to 0.5. So this is the estimated value. So that's what we are going to talk next week. So that's very good. Okay, so I think we spend some time about this some general principles. So later we can go quicker, about why we have to do sampling, why we wanted to find the sampling distribution. Because for this estimation, I wanted to know, sometimes we wanted to have a range. This value, of course, is not 0.5. But how likely? Sometimes we what's the interval? This like a point estimation. We wanted to find an interval. So we need to know the distribution. Basically, as I said, now this one become a random number or random variable. Because of the average replication, we may have, we cannot make sure have a fixed value. And then, of course, this one become a random variable. We wanted to find out what's the distribution of this random variable. And then we can talk about how good is this estimate, we use it as an estimate of the p here. So that's why we have to talk about the distribution. And then we basically we already cover everything of today. We talk about the sampling. You draw a sample. You draw a sample. We didn't mention this too much, but I just said that later we will see. This one has a distribution. Has a distribution. So sometimes we can, treat it as a normal distribution. This is the P. It's a normal. It's not exactly, but it's very very close. So that's the sampling distribution, and we talk about the parameter estimation. So the parameter here is the P in this box. And the estimation, you give the estimation. This is one estimation. And, once we have the sample, once we have the data, we can have a value of P. So basically, we talk about everything. Okay. So now, after that, I think we are clear why we need to talk about a population. Population many times it have an infinity sets. We only draw a limited number. So sometimes if the experiment is not very expensive, we can have a more replication. But sometimes the experiment may be very expensive, so we cannot have a much larger larger sample set. So the population we can treat is a infinity have an infinite number of individuals. Okay. So a sample is just a limited number of individuals in this box. And the number we have here, we can call it the sample size. Okay, that's the sampling. We wanted the sample, of course, we wanted to draw estimated p-value in this box. We mentioned this. Well, every time the sample must be representative to the whole whole population. So the principle of sampling is because every sample comes from the population. So before we draw that sample, if we talk about the distribution of one specific individual, before we have the observed data, so that the individual is from the population. Of course, if we talk about the distribution will be the same as the population. So we always said this samples have to be independent. So there's the word called IID. It's called the identical independent distributions. Of if we see this sample as a many number of random variable. If every sample is as a many number of random variable. If every sample is once we have see the data, it's a random variable. So that's the definition actually about a random sampling. in most of the case, once we have the random sampling, we can do some do some estimation. We can investigate, the property of the estimations. So let's see if they feel the population for this maybe, yeah, it's randomly drawn, randomly. Which means, before we draw the sample, everyone have the equal chance to be drawn, right? So because, before we, of course, once we have the sample, that's called the realized the data. Before we draw the sample, everyone have the equal chance. There are some sampling methodology, systematic or stratified, many times the population is not just the one, it's a mixed population. So today we just talk about one population. It's a binomial distribution. So sometimes we always have the population is not that simple. It's a mixture population. Let's say we want to find the human height. Well, then we know the men is taller than the women. So basically, that's the two population. The men can have a distribution, the women can have a distribution, right? So if we talk about the whole human being, so maybe it's better if the men and the women have the ratio is equal, 50-50. It's better when we have the sample. In the sample, we have 50% of individual form of women, 50% from men. If we have 10% of men and 90% of women, we will be misled if we do some estimation, right? Because the proportion of the two populations, is not the same, in the sample. So that's why sometimes we use the stratified to make sure so every population can be represented. Anyway, that's about the sampling technology. So now let's forget about the sampling. Now we have collected data. Now we talk about how to do the estimation. So before we talk about the binomial distribution, so we just have a number of black divided by sample size. So many times we may have the data. It's not really black and or white. It's a number. It's a plant height, or the maturity. So for this sample, now let's say we have the observed data for every sample. So we can do some estimation. We can do some calculation. So first issue, we can find the mean of the sample. So basically, before this estimator can also treat it as the mean of the sample. This actually it not look like on average, but actually it is. If we have the 5, if n equal to 5, if we draw one by one, so everyone, the black number, first the one we use B1, second one with B2, third one with B3, and B4, B5. Of course, for everyone, it can only be one black or white. So if it's black, we give 1. If it's white, we give 0. Okay? So let's say we have this one is white, it's 0. This one is white, it's 0. This one is black, is 1. This one is 0 again. This black is 1. So basically, if we see, this estimation or this, experiment as we have 5 samples. So this like the sample the value of each sample. So basically, if we add them up, so that's the total number of black, right? So basically, this can be read B1 and B2, B3, B4, B5, and divided the number of sample sets. So actually, yeah, the estimate we saw before, it's a kind of average. But in more situation, the X, it's not this. We know it's discrete, right? And many times it's continuous. It's like a green yield or human height, or the body weight, etc. So from this data, we can find the estimation. The first one we call the sample mean. So last week we also talked about the population mean. So this sample mean actually can be used as an estimate of the population mean. This sample values can be used to estimate the population variance. But in statistics, that's not enough. We also want to know how good is the estimation, like here. So that's where we also need to know what's the difference, what's the distribution of the sample mean. Because this sample mean, if we take the sample, each sample as a random variable, this again is a random variable. So we can talk about the distribution of the sample mean, right? So we can also talk about the distribution of the sample variance. Only if we don't know the distribution, it's very hard to talk about, how good. If we use the sample mean to estimate the population mean, how good if we use the sample variance to estimate the population variance. So that's why, this today we also talk about, the distribution of this estimation. We can also group our data. So again, take the example here. We can make a group. So the group here, of course, only have how many groups we can make here. Yeah, exactly. 2, because it's discrete. Then what's the frequency? In this sample, what's the frequency of 0? What's the frequency of 1? 3. Yeah, so exactly. This one we count have 3. This one have 2. So we can so this frequency is a count. So sometimes the frequency can be divided by sample size. So then we do the standardization. So this one divided by 0.5 is 0.6. This is 0.4. So we can say there are 60% of 0 in the sample, 40% of 1 in the sample, right? So this is exactly the F here. So if we add them up, of course, this is the sample size. This is equal to 1. But if it's not equal to 1, it doesn't make sense. That's because we like a probability. We consider everything. When we consider everything, it becomes 1. So when we make this table, how we find the mean? We use this 2 value. How we can find the mean of the value of the B, or the mean value of the 5 samples. We cannot just add 0 with 1 divided by 2. Can we do that? Yeah. Yeah. We have to consider the weight. It's a weighted average. So basically, when we consider the average, because this one have more, this one have the smaller. So basically it's a 0 by 6 and 1 multiplied by 0.4. So this is the exactly it's the sample mean here. If we make a group, if we do some frequency distribution on our data, so this again, applicable to continuous distribution. Continuous distribution, of course, we can have the group can have a set. This is for the discrete. I hope you can remember this. And based on the frequency data, we can have the estimation of the sample variance. So these are the two very basic. When we talk about the distribution, we said that that's some characteristic of the distribution. So here the sample mean, sample variance of the two very basic. The called the sampling statistics. The sample mean we can be used to estimate the population mean. Sample variance to estimate the population variance. So now a little bit more about the distribution, because again, without the distribution, we don't know how good is the estimation. Without the distribution, we cannot do any inference, hypothesis test. As you asked, we wanted to find, we have an estimate with equal to 0.2, but how likely, how whether that the difference of 0.2, is significant with 0.5. So to answer that question, we need to know the distribution of the sample mean, sample variance. We need to remember that, okay? So these are the three conclusions. Of course, this can be proved by mathematician. I don't ask you to prove that, but at least we should realize that conclusion. So first one, it says that the sample mean and the sample variance, they are independent. Because as I said, the sample mean, sample variance, they are again random variables. So we can talk about whether two random variables they are correlated or have some relationship. So first the one actually tell us these two they are independent. So independent by independent, of course, the in probability there are some definition. So if we talk about the joint distribution, so the joint distribution actually can be found from the distribution of the two. So here, remember that. And the second one is even more important. It tells us what's the distribution of the sample mean. So can you guess what's the distribution? If the population is normal, that means if the population where we have the sample is a normal distribution with a mean of mu, variance of sigma square, what's the distribution of the sample mean? So if here the sample mean again is a normal distribution. Remember this, okay? Remember this. And the normal distribution, as we said, it has one mean and one variance. So the mean of this distribution is equal to the mean of the population. But the variance is the population variance divided by the sample size. So what does this mean? Actually, this tells us how good is if we use the sample mean to estimate the population mean. Because this one actually on average, this again the mean is the mu here means the expectation of the sample mean. So if we can draw the sample for many times, Let's say here we repeat this experiment for 10 times. Sometimes with 0.2, sometimes with 0.4, but we consider the average of the 10 estimate. So the average can be exactly if the number of replication is large enough, the average actually is equal to the population mean. So this we say that it's unbiased. The sample mean as an estimation of population mean is unbiased. So what does unbiased mean? Unbiased means if we can repeat for many times, so the average will be equal to the true value. So that's called unbiased. Here actually it's said that the mu actually is the expectation of a sample mean. So that's why we said that the sample mean as an estimate of the population mean is unbiased. Because the expectation is equal to the parameter mu here. But take a look at the variance. The variance become much smaller, right? Because it's divided by sample size. The sample size at least if we just have one, it's equal to the population sample size. If we have more than one, so the variance here is always smaller than the population variance. So what we can see from this variance, if this variance is very large, it's good or it's not good as an estimate. So here, of course, for the population, sometimes we cannot control the variance. But here we can control. How we can control the variance here? How we can control this? Let's assume sigma square is fixed. How we can change this number here? Nobody knows. No, I mean the variance is fixed. But for this one, the variance is fixed, but when it's divided by sample size, it's not fixed at all. So this one is fixed. But I'm talking about the variance of the sample mean. How we can change this variance? Yeah, it's just as simple as that. If we have 2 samples, it will be half. If we have 3 samples, it's just 1/3. If we have 4 samples, we can just have 1/4. If we have 10 samples, we just have 1/10. But these are different. Sigma square is always positive, of course. So which one, as an estimate, do we wish to have the variance here is big, or we wish it small? Small. Yeah. Why we want it small? Yeah, exactly. If this variance is small, which the sample mean have a less variation. It's more close to the population mean. If the variance is big, sometimes let's here if we only have 5 sample, even though the true value is 0.5, sometimes we have 0.1, sometimes we if we have 5 sample, this is impossible. Sometimes we have 0.2, sometimes we have 0.8. It's the variation. If we talk about the variation, this variation is much larger. But if we have a sample size 10, so the value may be more closer. Sometimes it is 3, sometimes it is 12, and Of course, it can also happen for 0.7, but this variation is smaller than the variation here. So in one estimation, basically, if this variance is small, so the sample mean is more closer to the population mean. That's what we want, because we want to estimate the population mean. So if we have we put the estimation is more accurate. Okay. So remember this. If the population we have a normal distribution, remember the distribution of a sample mean. Okay. So it's as simple as this. Don't forget. That's the least thing in statistics you should remember after this class. So this one, it's okay if you cannot remember, but when we wanted to test the some variance, we have to know. So it's about the distribution of the sample variance. The sample variance when divided by the population variance multiplied by n-1. N-1 have another name called the degree of freedom. Okay. And this one have follow a chi-square distribution. Okay, now let's take a look about the chi-square distribution. So this is the chi-square distribution with different degree freedom 1 to up to 9. The larger the degree freedom, the tail is become very long. But the chi-square distribution actually comes from a normal distribution. So it's a square, it's a sum square of the normal distribution which are independent. And then we will have a chi-square distribution. T distribution. So all this distribution we talk about, is for next week. We wanted to do some hypothesis test. If we don't know the distribution, we cannot find the probability. Basically, the hypothesis test, form the distribution. Again, we can find the probability based on the all the significance probability. Based on the significance probability, we can test whether the non-hypothesis is true or false. Okay, the T distribution. So what is the T distribution? So the T distribution actually is a ratio. So the here is this is a numerator, right? The numerator, right? Or you call this one denominator. So the numerator is then the normal distribution, and the y here actually is a chi-square distribution, and divided by degree freedom will make a square. This will define a T distribution. The T distribution, we use it to test the population mean. Whether the population mean is equal to a given value once we have the sample. The T distribution when the degree freedom is large will become a standard normal distribution. So when the degree freedom is small, so the tail is very long. F distribution. So F distribution is again it's a ratio. It's about a 2 chi-square distribution. So the chi-square distribution we see it as come from the sample variance. So that's why this one can be used to test the significance of variance. which is commonly used in ANOVA. In ANOVA, okay. There are some relationship, I don't want to really go detail about that. The relationship between for the binomial distribution, of course, it's a special case of a 2-point binomial distribution. Sometimes can be approximated by a Poisson distribution, and they give the relationship of all the distributions. Some are very closely related. Okay. So yeah, basically we talk about a statistical inference now a little bit. Yeah. And without actually, yeah, without the all the distribution we talked before, it's for this purpose, which we will talk about next week. So now we talk about the parameter estimation. Of course, from the sample we can have the sample mean, sample variance, but many times we want to estimate some unknown parameters in the population. So there are two general classification for the estimation. So first one is a point estimation. Like before, we draw a sample, we know the number of black, we can have one value of p, but sometimes we can have an interval. Of course, we know if we have this estimate, it doesn't mean the true value is 0.3. The true but we wanted to make a range. How likely the true value is between 0.2 to 0.4, with this value in the middle. So this like the an interval. So we want to find an interval which give us the probability. Of course, we wanted to know the probability. The probability, let's say maybe this one just have a probability 0.5. But if we make a range larger, so the probability, of course, is larger. So this like the interval estimation about the unknown p with at this significant level or the probability level. So once we have an estimator, we can make a statement. I'm 90% sure, I'm 95% sure the p-value is located between 0.1 and 0.9. So that's the interval estimation. It actually tells us, based, of course, if the interval is large, the probability is large. But the interval is large, sometimes we don't like that. We want the interval as small as possible. That's again, only the population size can do that. But if we wanted to find, tell me an interval that the true value is that interval is 90% for sure. So that's sometimes the question you want to ask. Okay, so the point estimation, the theta is represents any parameter. So let in the binomial distribution, the theta is p. In the normal distribution, the theta represents the mu and the sigma square. Okay, so this is the general representation about the parameters in the population. So if we can make a little like a function, so we make this function, then for any sample, observed sample, we can have an estimator for theta. So this is called a point estimation. So the simple one is for the point estimation for the if one parameter is the population mean, basically the sample mean is the estimator of this parameter. We wanted to find out. But how we before it's just a guess. We yeah we this is the best guess. The estimate should be equal k divided by population size. But is there any rule? We want to find some general procedure to estimate this parameter. So there are two general methods to have that estimation. So this actually is the most commonly used that we call the maximum likelihood estimation or the maximum likelihood method. So actually Fisher made a great contribution to this estimation as well. So another one is called the moment method. Hope we have some slide. Yeah. So the maximum or MLE. So MLE basically means because every sample have the same distribution with the population. So if we consider all the sample together, we will have the so-called the joint distribution. So here is like the joint distribution. But here we don't call it a probability, we call it a likelihood. Because the probability means, we know the theta. We wanted to find the probability, for this variable to be different values. So here is the opposite set. We don't know theta. Theta, are the parameters we want to estimate. What we know is the sample size. So it's, as I said, it's the opposite thing. So we don't know the parameter, we know the sample. So this again, this function we could give a name likelihood. Likelihood basically it's very similar to the the density function or the probability. But the probability, it means we know all the distribution. We wanted to find the so you understand the difference here? No? Are you lost? So last week we talked about the probability. So for probability, we know everything about the distribution. We know everything about the population. So we want to find the probability for the random number, with a given value, or at a given range. As here, we know the p. We know n. We wanted to find what's the probability if k equal to 1 or 2. It's like that. We know everything about the population. We wanted to find the probability. But now is we don't know the p. But we know we have observed the value. We know the k. We know in this case the k is equal to 2. And then we can also write a function of this basically the function here is exactly same as the binomial distribution. So do you still remember the probability distribution of a binomial? Who can remember that? The p is a given value, and we have sample set is n, and we have the number yeah, n is given for k, have the possible value from 1, 0 up to n. So you know this probability is what? It's C n k p k. So this one we know this, okay? So we know the p here, we know the n here. So for any k, we can find the probability. So that's what we talked about last week. But now we don't know p, but we know k. Okay, because we have the data. And the problem we want to estimate p. So basically the function here is the same, but we give another name called it likelihood. Because if we treat as this function, now let's see, this is known, okay? Because we have the sample. And this can change. But it doesn't mean that this is a random number. It's just some value we don't know that before. We wanted to estimate. Of course, the p, we can put the p equal to 1 or 0.1 or 0.2 up to 1. Then for different p, so this function will give us a different value, right? Because n is known, k is known. Of course, for any p, I can find this function. So I can draw a line. I don't know exactly how the line looks like this. So this we call the likelihood function. So this is the p value. This is from 0 up to 1. Of course, here it's not really a line, it's a bar graph. Okay, for simple, I just draw a line. Because here, let's say we put a k equal to 2 here, k equal to 2. So that's the number we observed, okay? So here we put a 2, here we put a 2. So, and we put a 5 is known. So, and we put a 5. So there's only one variable here, which is what? Which is the p. Okay, so that's exactly we let the p change from 0 to 1. We can draw a profile or graph. So this is exactly maximum MLE means what? MLE means, yeah, this function when we see a maximum at this point, okay? What is the function? We can draw that. So we can see where this function can reach the highest value. So at this point, of course, there's the p here. So that's exactly the estimate we wanted to have. And this is why it's called the maximum likelihood. Because at this point, this likelihood function reach the highest value. Clear? Are you okay with this? Where is not clear? Yeah, it's a function. You can draw. Actually, you can skip this because it's a constant number. So you just let the p change, and then you draw a you draw a graph. In this graph, the somewhere the graph can reach the maximum value. So at this point, the p value is what we call this p value is called the MLE of the p we want to estimate. Okay. So this actually it's complicated, but if we talk about a specific distribution, well, it's not complicated at all. So now my point is, the MLE become optimization. How we can find out? Of course, you can for any function you can try different value. You can see where the maximum value is reached. But there are some general mathematical methods. You can find the maximum value here. Then what is it? Yeah, we just find that the derivative. And the derivative, of course, sometimes the derivative is very easy to have, sometimes it's not that easy. Let the derivative equal to 0, which means, derivative equals 0, actually, it's the maximum point. We don't go too much in detail. We don't like it. No. Some example about the normal distribution. So this is how the likelihood looks like. Now there are two parameters, and sometimes it's not easy to find the derivative directly. So we can make a logarithm transformation. It's like a logarithm transformation, because the likelihood is always like a multiplication. So after the logarithm transformation, it becomes additive. We know the additive is much simpler than multiplication, right? We learn addition, subtraction first, and then we learn multiplication and division. Okay, so normal distribution, actually the maximum likelihood MLE of mu is exactly is the sample mean, but the variance, there are some difference with the sample variance. What's the difference here? What's the difference of this estimate with the sample variance? Can you see it? You be focused. You remember here? Your degree freedom is n minus 1. Now it become 1. So that's the difference, between the MLE of variance with the sample variance. Okay. Anyway, we will skip the moment method. If you want, you can try some exercise. So the moment actually means, the variable, the variable, have the what do you call, how you call that? It's a exponential. So here it can be 1, so that's the expectation. If here is 2, that's the second order moment. It can be 3 and 4, so that's called the moment estimation. Okay, there's some. So how we sometimes, once we have the sample, we can give different estimation. So how we judge? So these are the criteria, to specify, the property of the estimation. So it must first, it should be unbiasedness. So this is easy to understand. If it's biased, how we can trust your prediction. So the effectiveness, which means all the information in the sample has been used. Yeah, there's some measurement about the effectiveness. Sometimes maybe let's say if we have a fed sample, we just use 4 of them. Some sample not used. So the minimum mean square. So it's like the represent the if this error is small, which means it's more accurate. So this is some general. So the definition of unbiased effectiveness, means the variance is smaller. Variance is smaller, which means the estimation is more accurate. Minimum mean square. This sometimes it's not easy to find out because many times if we don't know the true value, actually we cannot estimate this mean square. But this index sometimes can be used for the simulation. During simulation, we know everything. So through simulation, we can compare which estimate have the minimum mean square error. The interval estimate, actually, we find an interval, and of course, in statistics, everything, nothing is 100% sure. Okay, remember that. So we need to say, if I want to be 90% sure, you give me a range of the estimation. So this is something like that. If alpha is the like the 5% or 10%, if I say I wanted to be this much sure, give me a range of the estimation. So that's called the interval estimation. Yeah, basically this is also important. We sometimes a lot of people ask about what sample size should I have? How many replications I should I make in the field? To answer that question, actually we need to need to have this interval estimation. And we also need, the type 1 error, type 2 error, which are, we'll talk on next week. So I skip there are some slides. There are two laws in statistics I think you should realize. So first is the law of a large number. So law of a large number, which means for any distribution, it can be normal or cannot. For any distribution, actually, this law tells us the sample mean is always a good estimation to the population mean. So because this don't be scared, it just to tell us, if the sample size is large enough, the sample mean can be any closer to the population mean. It just means that when the sample size is large enough, the sample mean can be any closer. So this you can see that as any closer. So this probability is 1. So that's pretty good. The sample mean, so that will probably is the most frequently used estimate. The central limit theory tell us, the sample mean, if we made the standardization, make a difference between the population mean and divided by standard error will give us a standard normal distribution. Again, it doesn't matter what the true population is. So the sample mean after the standardization, it will become a standard normal distribution. We'll also be aware of the small probability event. This again is the interface hypothesis test is based. So what does it mean? So it means a small probability event is less likely to happen in one experiment. So if the probability, let's say, if here the prob k equal to 0, and the probability if from this normal distribution, let's say we find is 0, 0, 1. Of course, how small is small? It's you can argue that. So if we see this is small, is this small? I think most of them may say it's small. The some of you maybe I don't think it's small. I only think this is small. That's okay. And then we talk about the p-value at this level. Okay. So this is we call the small probability event. This event have a very small probability to happen. So this principle tells us that if I only make one experiment, this is less likely to happen because the probability for it to happen is only equal to this. So if I draw one sample, I only make one experiment, and I can say this event cannot happen. Do we agree? No? Let's give you another example. If I draw the cone, if I draw a cone, okay, I can either have see the top or tail. So you can find out the probability for if I draw 10 times. Every time that I see the tail, I think the probability is 5% up to 10. Is that a small? Do you think that's small enough? Then it means if I only draw one replication, actually it shouldn't happen. You have to understand this. Otherwise, this everything. This is all in the hypothesis test is based. Response. Okay, so we take a break. After that, we do some exercise together. Hopefully, you can give you more idea about the distribution, about the sample. The thing is, we can do some simulation. We can simulate some sample data, and then we find out the sample mean, sample variance, and we can also do some there's some data transformation. So from the we can draw a sample from distribution and see how the sample mean and the sample variance are distributed. So that's the that's the major topic. So for those if we use the advanced Excel, actually it can draw generate the random sample for a lot of distributions. If your computer don't have that, but at least every computer should can draw the a uniform distribution. So which means it's a uniform number from 0 to 1. But after we do some data transformation, we can have standard normal distribution. From the standard normal distribution, if we add something and multiply by something, we will have have any normal distribution. So maybe first let's try this. We use the random number generate in Excel, which is called RAND, to generate the a random value from 0 to 1, and then we make a transformation, and then we take a look how the transform from the data point looks like. So this is like some simulation work. Let's see. I want to open. So if you take a look at the Excel, so first one I just the draw some random number and make a frequency distribution. Uh, so maybe I remove this, so we can start from the beginning. So let's say yeah, it's shared. What's up? So here actually there's a function to generate the random number just round, and then you give a bracket. So this function you don't need to have any other input. So you just enter. So you drag it down. Let's say we want to generate 100. So you just drag down and drag to the left, to the right. So we have but the 100 value you have maybe different as main, doesn't matter. So now this is simulation. So let's say we make an experiment and now we immediately we have 100 observed data point. Okay. So this data point, so this Excel basically if you change anything anywhere, if you enter the random number also changed. So how we can fix this. So sometimes once we generate the random number, we don't want it to change again. So when you do that, you do Control C, and we fix the fix the here. So here we just do copy paste. So you select the 100 the cell with the formula, and then you Control C. But paste here, you need to the paste also have a lot of options. So here we just use the paste as a value. So here we select the first place we want to put the value, and then you do paste the value. And now as you check here, now you cannot see the formula. What you see is a value. Here actually if you do enter, if you change, I think if you change anything here, you will see this part is automatically updated, but this one is fixed. So because we fixed the value. So you know how to use use that too. You do Control C, and when you paste, you select some options. So here you select that we only paste the value. Random is just the random, RAND. Yeah. random, and then you just drag right, drag down. So now let's say we wanted to make a frequency. We wanted to make a frequency graph on the 100 data point. Okay, so all this value I make 10 groups. So the group value is from 0 up to 1. It's the group size is 0.1. So you remember how to find the frequency here? I remove it. So the frequency here, we select because we every group has a frequency. So the frequency not just one. So the frequency will take these cells, and then we click frequency. Okay, and then we select the 100 data. Of course, you need to tell Excel, how we do the grouping. So this is how. This is we group our data, and then Control Shift Enter. So we will have the frequency. So in theory, every number, it should be 10 on average. But some cell is some more, some less. Oh, it's a little bit strange. So, and then you draw the bar graph. You select the frequency. You do insert, and then you draw the bar graph. Of course, I think you should be able to change it, give the title of X. I think that's here. And here you can change a lot of things. You can give the title of your figure, title of X, title of Y, etc. Okay, so basically that's what we did before. So we draw 100 random samples from this distribution, and we draw a frequency. Okay, now next we draw the sample from the normal distribution. So this normal distribution, the mean is 10, and the variance is also 10. I think we just this table we have 6. So after the class, actually you can transform the data analysis. Yeah, maybe we just try here. So on the field, give actually the normal distribution is generated from a uniform distribution by using this transformation before. So now we just I will open a new Excel sheet. So we just use the data analysis to draw, let's say we have a 5 samples from this distribution, but we want to have 100 set. So 100 set. I will remember write some title here. This is sample 1, 2, 3, 4, 5. And this need to replicate 100 times. So if we have a random number here that's just the one set, like a one experiment, we have the 5 observed data, but we have in total have 100 because we want to see the distribution of the sample mean. So how we do that? Let's see. Let me try first. I think I will select the 100 by 5 in my computer. Basically, I go to 101. It will make 100. And I click data. Do you still have the data analysis in your computer? If you don't have that, you need to go to the to have it out. We click anyway. I don't know where it's in your computer. It's called random number generator. So this is like we make some experiment. Let's see. I think I can put here 100. Anyway, I'm not sure. We can try again.
Random number generation.
Generator or generation, could be generation. Anyway, you see this interface. And then you click the distribution, because we are going to simulate a normal distribution. And then you select the mean, and the mean is 10 normal distribution. So here it asks for the standard deviation. So our variance is 10. So standard deviation, what's the square root of 10? No, square root. Square root. I need to find the I don't think you can input the function. I just square root 10. Okay, it's 3.16. Okay, now I go there again, and random number generate, and 510 normal. So this is 10. This is just the input 3.16228. Anyway, here I think you can leave it as blank. And then here we select the range. I think we can just select the starting point. Let me try first. Let's see. Okay. Yeah, actually that's exactly what I want. So we generate how many? Actually, it's 500 random number. So this is like we do the experiment once. We have the 5 of the data. Another time. So again, in real case, that normally we only have one repeat. But this is a good thing in simulation. Okay, do you have the data? Square root the function called sqrt. Yeah. Okay. If you are ready, actually next we want to see how the sample mean distributed, how the sample variance distributed. Okay. Which function?
From data analysis.
Okay, you are still there. Data analysis, random generation. So here you input the 5 because it's like in one repeat we have a 5 data point, and we want to replicate 100 times. So here you select the normal. Here you input the 10 and 3.16.
Why we put 10?
10 is here is the mean of the normal distribution. But we want to simulate this normal distribution. So this is square root of 10. So this again, because this is the mean of the distribution, is standard deviation of the distribution. And here you don't need to. I think if you keep it here as nothing, if you do that next time, you will have the same data point. So if you don't want to see same data point, one time you change the number, and then you will have a different value. This is like the random seed, random seed your simulation. So let's see, we just don't use that. And here, you click this button, And then because we have a lot of data point, we wanted to, give us some space or place. So here I just select the first one, and then you click OK. Anyway. Now you have the data. Okay. Okay. Now we can. Different. Because this is random simulation. Yeah, it comes from the same distribution. Of course, it's a different computer have a different random seed, so this is normal. But later, when we see the distribution, your distribution should be same as mine. This is for the the data point. Let's say here we want to find the sample mean. And this column I want to put the sample variance. Okay, please follow me. Sample mean. How could we find the mean of the 5 data point in Excel? We did that average. Great. Average, and you select the 5. So that's a sample mean for each sample. So we have 100 sets of sample. So the sample variance you just VAR. The VAR, as you can see, there are 2 comes out. Oh, no, not 2. It's many actually. The P, the first 2 and the last 2 actually the same, just for different versions of Excel. So the first 2, the difference is is the degree of freedom. Exactly, the VARP is like the maximum likelihood estimation. It's the sum square divided by sample size. This one is sum square divided by n minus 1. So that's the difference. Here we want the sample variance. We click the second one. So you can understand the P as the population, okay? S as the sample. So you can, then it's easy for you to understand. We click VARS, and then we select the 5 number. So we have the mean, we have the variance. So as you can see here, that's what I said. All these data points come from the same distribution. But this one we don't have the mean is 1.5 lower. The variance is much lower. But this is just the one situation. Let's see what will happen for other replications. You select the 2 cells, okay, and then you drag it down up to 101. So immediately we have all the, of course, we see sometimes we have more than 10, sometimes again the variance can be more than 10. But basically, I think as I said, this sample mean is unbiased. What do we mean unbiased? If we add the 100 up, please guess. It should be far away to 10. If we add this one up, it should be close, very close to 10 or far away. Anyway, you can try. let's say I just put, the average of the 100 sample means. Okay, it's close enough. Okay. So I just find the mean of the 100 sample means, mean of the 100 sample variance. Now this is what I said. Sample mean is unbiased. Sample variance is also unbiased. Think about that. If I have 1,000, it can be, very, very close. So this is why I said this is unbiased. What does unbiased mean? Okay. The true value is 10. So do you think it's closer to 10, or it's close enough, or still not that enough? What value you have? I think even though your data point is different, but this true value you should also have 10. No?
Near.
Yeah. Well, not again. The 100. Here I talk unbiased when when I go from 100 to infinity, then it becomes exactly 10. But it's closer to 10, right? But how the distribution looks like? This is just the mean of the, we can draw the distribution of a sample mean. We can draw the distribution of a sample size. Okay, now let's draw. Okay, as I said, here, this is in theory the distribution of the sample mean. It has a mean of 10. We already see here. How we find the variance? How could we find the variance of the sample mean? How could we find the variance of sample mean? So basically, it's variance of these 100 values. Try to find that to see whether it's closer to 2 or not. If it's not close to 2, means something is wrong with you. It's VARS again. And the variance of sample mean is you just use the variance and you select the 100 sample means. Enter. What do you have? Anyway, you may have a 2 point something, and I have a 1.9. So this is the true value, but with the 100 replications, that variance is closer to this true. So that's what we said. The distribution of the sample mean, have a mean of 10 and a variance of 2. Okay. So you can continue to find let's see. Let's find the draw a frequency distribution, and we can compare with the theoretical distribution. Let's do one by one. Let's draw a frequency distribution, and then we draw the theoretical distribution of this normal to see how fitted they are. So we draw the distribution we want to find. Basically, we want to make a frequency distribution on this 10 point. So normally we don't want to miss anything. So this is the option you can use. First, you find the minimum value and the maximum value. I mean the minimum of the 100 sample mean, maximum of the sample mean. So we can make some groups. Okay. So this is what we are going to do. We are doing now. You do the minimum, and then we select the 100. So more important, you should realize what are we doing for. It's not just like this. We should more important. We should understand what does this value stand for. Why we do that calculation? With the 500 values, we can do lot of estimation. We can do lot of calculation. But we need to know which one makes sense. So here, why we wanted to find the mean value and the maximum value. Yeah, somebody maybe can tell. This is the same, when you collect your data, you want to make a frequency, you should follow exactly the same step. You find the mean value, you find the minimum, you find the maximum, so we can make some group. So what's your minimum value and maximum value? I think yours should, this also, everybody should be similar, around 7, okay?
6, 7, yeah.
Yeah, anyway, it's almost, maximum should be, this can be very much different, but here, some of the rules we see, the distribution we see, should be same. Anyway, if you have a 6, and then you can make a group, maybe let's assume we have some value at a 6. So we can make a group from 6 and 7, 8, 9, 10, 11, 12, 13, 14. So why we make this group? Yeah. So if we make this group, actually all the 100 will be for, can be classified. Yeah, in this region. So let's say we can make this like a group. You can give a name. I say this are the frequency. Again, we used this function before. You select the cells to enter frequency. And then what do we select? Because we want to see the frequency of the 100 sample mean. So this always, don't just follow me, do this, do that. More important, why we, why we select that, why we calculate that. So every, what we are doing should make sense. We select the 100, so yeah. And then you do Control Shift Enter. Oh, sorry. And then you need to input the group information. And then the Control Shift Enter. So how we find the percentage? Is a number. How we find the percentage of of the data point in each group? Yeah, it's the frequency. Now that the 100 like the sample size. So we are talking about the distribution of the 100 sample means. So we find we drag it down, so we have the frequency. Okay, now let's put the true distribution. I hope everybody can follow up to now, right? So now remember so this is like the theory. So in theory, the sample mean should have this distribution. Now I want to compare. So let's put the theory distribution, how we find out the frequency. So now that it's a theory, we should use the normal distribution as we used the last week. And we input, let's see, we can know it's the x here. It's the mean is 10. The variance, still remember, is 3.1, I think it's 1/6 summation, right? Anyway. Here, what should we use? We select the true or false. True, what does the true mean here? So this is the normal distribution. What does the true mean here? Well, because well, even you use SAS, you still understand this. It's the normal distribution. Let's say this is 10. So here is 10. The variance is 10. So if we say here is 6. So now what we are doing, of course, there's a function here, px. And you still remember. Anyway, so this is the function of this curve, and here is 6. So what does if we select the true there? What does the
If we select true, then it means our data should be in between 6 and 10, right?
please remember here the now is I5 is 6. 10 is the mean of the distribution, and another the 3 actually is the square root of 10. Okay, now well let me end. So what does this value tell us? Is 0.5 summation. 0.5 is what? It's Is this height or some area? It's a probability. So the true is it will give us the probability. So what is the probability? And by using this curve, what is the probability at this level, at the 6, at this value? Remember, it's this tail area. Okay, so this is the area actually is the probability. Let's say here if I use force, what does force? If here I put a 0, what does 0 mean? Anyway, let's see the value. Actually, this maybe before I did the before I should input a 1. So if I input a 1, so it's the if I input a 1, so this is the probability. It's the area. So if I input here 0, which is the force, so what does this value mean? 0.5. Remember here I select the force. So the 0.5 is what? The 0.5 is just the height. Okay, let's see here. Here maybe 0. This is y. This is x. So now it's the 7-point summation is the height here is y there or the height here. Understand? No? Why? I don't know why it's that hard. Okay. So here, what we want? We want 1 or we want 0? Guess. So this value is more like a probability or like something like a density. So is this a probability? So probability is always accumulative. Once we have everything, probability should be 1. So this it can be look at the probability. It's a probability at some interval. It's a probability, in some group. It's similar like a density. It's not accumulative. If you want accumulative, you should add something up. So here actually we want the. So later I will see that there are some difference.
And again, when we need to set 0 and when we need to use 1.
Okay, exactly. So it depends on what you want. Do you want the probability? If you want the probability, you need to select the 1. You want only the height of this line, you select the 0. Okay, so if you select the 0, it's exactly this formula, what this formula tells us. If you select the 1, it's an integral. Integral form the minimum value up to this point. So that's why I said it's an area. Okay, so we then you just drag down. Okay. So as you can see, it's not exactly same, but maybe 100 is not large enough. Let's say if we want to draw these two lines together, we select the to insert. Anyway, what graph do you have? It fitted very well, or it's similar like a man. Yeah. So if we increase 100 to 1,000, it should be much more fitted. So there actually is another problem here. We should do some adjustment. For this f value, we should be plus. We should plus half. After that, it will be much better. So I think, especially if we have a very large sample, y plus half, because this value is actually is between 7 and 8. So this value, oh, yeah, this value actually is between 7 and 8. So the middle point, the middle group value, should be, is 7.5. So it's better, that's why here I do some adjustment on the back. Let's see what's the distribution here. Okay, for clear, I remove my figure. Now let's see. I remove everything here except the. Okay, now next let's see this distribution. As we said before on the slide. So this actually give you a chance if you don't believe some statistical theory, you do some validation. You can do some validation. Let's see where is it. Hmm? Okay, here we go. So next we basically I said that this is very important. So through simulation we see the distribution of sample mean, right? So the sample mean is the relationship between distribution of a sample mean and the population distribution. And then now we see the sample variance. Sample variance multiplied by n minus 1 divided by variance is a chi-square distribution. That's what we are going to do now. So here I make a note. It's n minus. Anyway, I just use this SS actually. Once we do this, it becomes a sum square. I do a sum square divided by VAR. No, maybe sigma square. Hmm. Anyway. And okay, what's the sum square? Sum square is actually sample variance multiplied by anyway. And okay, what's the sum square? Sum square is actually sample variance multiplied by degree freedom. What's the degree freedom here? What is?
100 minus 1.
No, I mean for the favor data point. I'm talking about the the sample variance, that's where the sample variance only form 5 data point. Yeah, it's 4 and divided by what's the population variance? The variance of the population. What's the variance of population? No, when we do the simulation, what is the variance of the population we simulated? It's 10, right? So here, divided by 10, actually give us this value. This value, if we consider all the 100 or more, it should be follow a chi-square distribution with a 4 degree of freedom. So next we find all the, for the 100 of this value. The 100 of this value. We just drag it down. We have 100 of them. Again, you find the minimum value. Like now we want to draw a frequency distribution. How does the frequency distribution looks like? Okay, you go ahead, find the minimum of the 100 values. We just find what is your maximum value. What value do you have? Okay, yeah, we should have a very similar value. Maximum map computer is 13. Usually we also have something around 13.
You have 1.38.
1.38. I mean maximum. So this column is the G column multiplied by 4 divided by 10.